Good evening, everyone. We are in the final summary session of the NPTEL course, Control and Tuning Methods in Switched Mode Power Converters. I am Teja, a fifth-year research scholar working under Dr. Santanu Kapat at Embedded Power Management Lab, IIT Kharagpur. Let me share my screen. Before I start, do you have any queries, or should I just briefly summarize what we have discussed, and then you will ask doubts if you have any in between?
Yes, sir, that will be better.
Okay, so I'll just not go in detail. I'll just browse through what we have discussed. So if you have doubts anywhere, then you just stop me and ask me. So today the session will be of 1 hour only. So it's a bit more of a summary session. And if you have any doubts, you can ask. So I'll not go in detail. I'll just go through or mention the topics that we have discussed and on based on like a surface level summary, not in depth. So this course is of course control and tuning methods in switched mode power converters, and in week one, we have discussed about a different type of voltage regulator before we move on to switched mode power converters. So we have discussed about series voltage regulator as well as shunt voltage regulator. We have seen what are the voltage gains as well as the efficiency expressions, and then we have seen the derivation. And we have also discussed about capacitor voltage regulator with and without resistance. And we have seen if we don't have resistance, then this is the expression. If we have resistance, then how we can get the expression? We'll have to solve the first order dynamical equation. And then we have moved on to switch mode power converters to start with the famous buck converter. And we have seen how the buck converter operates and how to get the output voltage and input voltage relation in terms of D, which is the duty ratio. Duty ratio is the fraction of on time to the switching time period. And then we have seen these waveforms, which are the steady state waveforms of a buck converter. And then we have also learned about volt-second balance, capacitor charge balance. And then the same thing we have done for the boost converter, where we also got the relationship between the input and output currents as well as voltages, and then the efficiency. And then we have done the same for the buck boost converter, and we got the similar type of expressions. And then we have solved few problems where I have given one circuit and I have asked how to realize this using MATLAB, and we have realized it in terms of one-way blocks as well as some gains and some constant blocks. Then we have asked you to find the Vx expression. So we need to see how Vx is changing when the switch is on and the switch is off. And then we got the Vx expression. And then we multiplied by Q and 1 minus Q to get the details. So once we got Vx, then we have moved on to another such problem, which is based on efficiency, a simple resistive divider. And we have gotten the efficiency expression. So these are all basic math. And then we have given one problem on buck boost converter based on the voltage relation between the input and output voltage. And we have seen how we can solve if it is operating in buck mode, if it is operating in boost mode. And then we have seen a problem on that. So any doubts in week one? Week one is just a simple introduction about switch mode power converters.
Sir, in week one,
Yeah.
other than this, that switched capacitor converters were mentioned briefly
Yes.
in the videos. So in that, the two circuits are given, step down and a step up.
Okay.
And that operation is clear.
Okay.
But if we want to derive the expression for output voltage, like what we did in buck and boost, those examples.
Yes.
So in those cases, we used inductor volt-second balance.
Yes.
So is there any thing like that in
yes, you can do capacitor charge balance. So basically, you assume the voltage across capacitor is VC1, VC2, and then the current is IC1, IC2. And then you see when the switch is on, like there are different modes, right? Q equal to 1, Q equal to 0. You see in which, like same as this capacitor charge balance. Say in first mode, what is the capacitor current? And then similarly, what is the current in the other what do I say in the other mode of operation, and then you can get the details based on current. Similarly, because they are ideal capacitors, right? So once say this type of connection is made, you know that the charge has to be same. So when Q equals to 1, say this is the type of connection that the capacitors are connected. Now you know that capacitors will charge instantaneously, right? So because they are ideal. First of all, we are considering about ideal. In the case of non-ideal, it will take some time. But the moment you connect C1 and C2, they'll reach the same charge like instantaneously. So the charge for capacitor 1 and charge for capacitor 2 are same, and then the charge for capacitor 1 is C into voltage. This is also C into voltage. From there you can get the voltage expression. So now what you can do is you can get the voltage expressions of capacitors when the switches are in one configuration. The moment they are converted to another configuration, again you have to solve for the capacitors based on this charge balance and then see what is the output voltage. So it will like in the case of practical converter, like the capacitors will charge, and then it will reach steady state. But ideally, it will happen instantaneously. Similarly, you can get the relation of the currents based on the capacitor charge balance. Sorry, where is the charge balance? This one, capacitor charge balance. So assume the currents, and then you can get the current uh, flowing through the capacitor average should be zero. So in that way, you can get the currents. Is that clear? Whoever has asked.
Yes, sir. But my doubt was, I saw that output voltage will be a multiple of two like that, 2
Yes.
VI or
So
4 VI.
okay. So what
So
actually they do is they charge the capacitors parallelly. Like say maybe I'll just not exactly the same thing. So what they do is the switching configuration they select in such a way that say you have two capacitors, they'll charge both the capacitors. Sorry. So they will charge both the capacitors to Vin. So the switching configuration is in such a way so that this is Vin and this is Vin. So now the switching configuration has to be in such a way that I'll connect these two, and this is my out. So this is plus minus. Now it becomes 2V. Similarly, if I have to get 4V, then I need to have capacitors charged to V for such capacitors, and I have to connect them in series so that my output is 4V. So this is the like overall idea of capacitors. If I want to have the fraction of capacitors, then what I will do is I will charge the uh, capacitors together, ideal capacitors. So both of them together are charged to V in because they are ideal and then they are symmetric. So my output I will get V in by 2 because both are equally charged. Similarly, if I want V in by 3, then I will have three capacitors. So here we'll get the discrete values rather than having, changing the duty ratio, such thing. So but the overall objective is this, like if you want to add or increase voltage, then you have to charge the capacitors and then parallelly charge and connect them in series. If you want fraction of that, then you have to charge them in series and then connect them in parallel, something like that.
okay, sir. Okay.
Okay. So now moving on to week two. Week two was more about designing the inductor as well as capacitor. So we have seen that inductor 30% ripple is the thumb rule, and then people consider 30% of the average inductor current and design the inductor. Similarly, capacitor 2% to 5% output voltage ripple they consider, and then based on that, whatever value we'll get, that value we'll choose. So in this lecture, I have also mentioned how to select the components. So I think I have also gone through DigiKey, opened the DigiKey website, and then showed how to select the inductors, capacitors, what are important. So if our inductance value, RMS current, saturation current is important, capacitor value, voltage rating, and something called derating is also important. Like how the inductance will reduce with the current, capacitance also will reduce as the voltage increase, voltage update across it. So this is called derating. So here there is this is happening because of the BH curve, and this is called inductor saturation. Here it is called derating of the capacitor. So if the voltage is high, then the capacitance value will become very, very small. So you need to consider that derating is all that derating also while designing the capacitors. And if you have any doubts, you can go through that lecture where I have shown how to select the capacitors. So now in this we have in this week we have solved numerous number of problems based on how to design the inductance as well as capacitance when there are certain conditions like inductor replace 30% if there is a range on V. So always we have to consider the worst case scenario. Means the worst case inductor ripple should be 30% of the load current. In the best case, it can be less than 30%. So the worst case ripple of the inductor current should be 30% of its average value. Similarly, the worst case capacitor ripple should be 2% of its average value. So in that case, we have to choose that value of V in and V naught where the worst case happens. And for that situation or for that condition, we have to design the inductance as well as capacitance. And then we have also discussed about discontinuous conduction mode, where if the load current is less, then we can operate in DCM to reduce the like losses, because here the RMS current will be more. Here we can reduce the RMS current, and we have seen that the critical conduction mode is when the average current of the IL is half of the ripple. So from this we can get the expression for critical conduction mode for all the converters like buck boost as well as buck boost. And here I have considered buck converter. I think Kelvin has considered boost converter, and we have solved a few problems on that. And then we have also discussed briefly about modulation technique, like here pulse width modulation, how to generate the gate pulse using the sawtooth. Now that you are familiar with this, I am not spending much time. And we also identified there are two types of modulation. One is trailing edge, and another is leading edge. And then we have seen how the waveform will look like and how we will get the set and reset pulses. So here I've given one question based on the trailing edge and leading edge. Then we have also solved a few more problems on constant on time, constant off time. So if the modulation is constant on time, how the duty ratio will change for a wide range of input, and how we'll decide the inductor current ripple, and how to select the inductance, etc. We have checked. So any questions in week two? So in week two, it was more of some understanding about design, choosing inductance and capacitance. And then I have also showed how to select the components online using DigiKey. Okay. If you don't have any queries, then let us start with week three. So in week three, we have started with practical voltage source, because whatever voltage source we'll get, it will have some parasitic resistance as well as inductance, and parasitic resistance as well as some capacitance. So now this has become a second order system. So we have seen what are the transfer functions, and based on the transfer function, we have seen that because it's a second order, depending upon the damping, it can be underdamped or overdamped. So ideally, if I naught is changing, VS is constant. But because of this additional dynamics, because of the parasitic, it will exhibit a second order behavior. So now it's the controller's responsibility to make sure that my output voltage is not changing even when the input voltage is changing. So this comes under the audio susceptibility. So it should have like a very good line rejection, which means supply rejection or line rejection. So when the supply is changing, the output voltage should deviate minimally, which my controller must ensure. Then we have seen how to implement this in MATLAB. I have given one question and we have implemented this in MATLAB by getting the equation. And then we have discussed about the objectives of the overall system, like what are the static objectives, which are ripple efficiency as well as power densities, and dynamic objectives is performance, voltage understood, and sending time should be minimal. And then operating requirements like EMI, power of sequence, how to start up, and then fault management and protection, which are under voltage lockout, over voltage, over current, and over temperature. We may not have discussed all the aspects, but we have discussed about majority static objectives, dynamic objectives, and how to design the controller. Sir has also discussed how to put protection and everything, but we have not gone deep into that. This is the overall circuit that Sir has shown. For a buck converter, we have signal processing. We have also discussed why signal processing is needed, because if there is any noise, we need to filter it before we send it to the controller, and then the controller can be feed forward or feedback control, and then modulation technique will generate the gate pulses depending upon pulse width modulation, constant on temp, constant off temp, but the overall architecture remains the same. Then we have seen how we can improve the line rejection, meaning how we can reject the input voltage disturbance in the output by using input voltage feed forward. We have seen that if we have input voltage feed forward, then my output voltage is totally independent of the input voltage. So in such cases, how to design the controller modulator we have seen, and here I have considered a buck converter under VFs. Similarly, if it is boost, then we have seen that it's a nonlinear function, so that may be practically very difficult to implement. And we have also seen how the V naught is changing if V in is changing, and then we got some relation between V naught and V in. And then here I think someone has asked certain doubt like what will be the first order response, what will be the second order response, depending upon voltage mode and current mode control. So this we have again discussed in detail in the upcoming weeks, but because someone has asked queries, I have told. In voltage mode control, we have 2 degrees of freedom. We can adjust both the damping as well as rise time or settling time. Whereas in the case of current mode control, it's a first order system, so it is overdamped. So we can only control the rise time because damping is already decided because it's a first order system. Then we have discussed about the voltage mode control architecture, that it's a single loop and how the gate pulses are generated and what are the individual blocks in the voltage mode control. Now that we are familiar, I'll just quickly go through the other one, which is the current mode control, which is a two-loop control. So in voltage mode control, the voltage is the single loop. In current mode control, we have two loops. One is the voltage, which is the outer loop, and current, which is the inner loop. And current loop is faster, voltage loop is relatively slow. Here we have seen there can be peak current mode control, there can be valley current mode control, which are also called as trailing edge as well as leading edge modulation. And then here we have seen how this is differing from this, and we have used the same color so that we can identify which blocks are same and which blocks are different. So majority of the things are same, except that here it is compared with the sawtooth, whereas here it is compared with the sense inductor current. Then we have seen the MATLAB implementation of current mode control, how it is being implemented. And then, as mentioned, we have discussed about trailing edge as well as leading edge, which are peak and valley current mode control. Then we have solved a few problems, but here I have asked the control architecture diagram. So how the architecture diagram will look like. So first we have identified and understood the leading edge and valley, leading edge and trailing edge modulation, and then we have identified the control architecture, because here the reset pulse is given by comparator, here the set pulse. Here set pulse is given by fixed frequency clock, here reset pulse. And here whatever is plus minus, it will be minus plus, because here in one case it is peak and another case it is valley, so it will be vice versa. So in week 3, it's all about practical voltage source and understanding the voltage mode control as well as current mode control architecture. If you have any doubts in week 3, you can ask. Okay. If you don't have any queries, then I'll quickly go through week 4. So in week 4, we have started with the constant on-time variable frequency. So we have seen voltage-based constant on-time control, and we have clearly understood why minimum off-time is needed. Because if minimum off-time is not needed, then we have seen that it can collapse. So we should have that forceful minimum off time when the output voltage is not charged enough. So then this minimum off time and followed by constant on time will try to give the converter some time so that the V naught is again charged and it will cross the V reference. And similarly, we have seen same is needed for the off time, but here we have seen the during step up, the minimum off time is needed before reaching into the new steady state. Similarly, for step down, on time is fixed, off time is variable. So here the response will be better for the step down response, because here off time is variable. Now we have seen voltage based constant off time, and here we have seen why minimum on time is needed. So in the case of on time constant on time control, minimum off time is needed. In the case of constant off time control, minimum on time is needed. And here we have seen that the step up response is better because the on time is variable. Whereas in the case of step down, there will be minimum on time because it's constant off time control. But if you use both, then the response can be better. And we have also seen voltage-based hysteresis control. And if we have VH and VL, how to calculate delta VH and how to calculate the time period as well, because the time period is varying depending upon the this ripple hysteresis band or the ripple. And then we have seen, like someone has asked stability of peak current mode control. We have discussed that peak current mode control is stable for D less than 0.5, valley current mode control is stable for D greater than 0.5. Whereas in the case of variable frequency, we don't have such issues. So variable frequency are better in terms of stability, because fixed frequency will limit the duty ratio of operation depending upon whether we are going for peak current mode control or valley current mode control. And then we have also discussed about split trigger and how we can get the band region for the Schmidt trigger and what are the relationship between V naught and Vn. So this is a positive feedback. So either it will saturate the op-amp to plus VDD or minus VDD. So depending upon the input voltage, it will either saturate to the positive side or the negative side. And here also we have solved few problems. Then I have explained few problems based on the constant on time, off time, the inductor design as well as the capacitor design, which we have been doing for many weeks. And then here I have given one hysteresis control, and I have asked what is the band and the time period, which we have also discussed. And I'm just skipping it. Then here I have given one constant on time control and then asking the switching frequency, worst case ripple, etc. Just the design problems. And then we have also discussed about the light load modulation techniques. So why light load modulation techniques are important? Because in order to improve the efficiency when the load current is small, we need to have variable frequency. DCM is one thing, but we can also have variable frequency. So we have discussed about adaptive on time. We have also discussed about the pulse skipping modulation, and we have understood how things are working and how it can improve the efficiency. And we have also understood how these things work, adaptive on time and everything. And we have solved one problem on the adaptive on time as well. So any doubts in week 4? So week 4 was more about variable frequency modulation techniques as well as light load modulation techniques, how the variable frequency can further improve the efficiency at light load conditions. Okay.
Sir,
So if
this
it, yeah,
RAM compensation was used
yes,
for overcoming this stability
yes, yes,
problem in peak
yes,
current
yes.
mode control.
So what
Okay.
happens is, as you have mentioned, in the peak current mode control, we have stability issue. So I can have external ramp compensation to make peak current mode control stable even when the duty ratio is above 0.5. But again, if you use the ramp compensation, you need to have high requirements of the ramp to make it stable. And then as Sir said, because now we are using ramp compensation, again uh, the pole that is sitting at like far away from the imaginary axis will come back, and then again it will behave like a second order system. So instead, like it will work like voltage mode control. Again, depending upon your requirement, if you can use variable frequency, you can use, because there is no such requirement of external ramp compensation because it is stable throughout the entire range of duty ratio. But maybe in your application you have to use peak current mode control, then you have to check whether the duty ratio is less than or greater than 0.5. Say, unfortunately, if it is greater than 0.5, you have to use ramp compensation. Is that clear?
Yes, sir. Is it correct to say that if we use RAM compensation, this bandwidth will decrease?
Um,
Uh,
we have to check actually. We cannot comment on that whether we can achieve, because like the RAM compensation is to stabilize whether it will affect the bandwidth or not. That we have to check. I'm not sure whether we can exactly comment on that, because I believe we can achieve like similar bandwidth even with RAM compensation. So I'm I think I'm like towards the that it is wrong because it's to stabilize the system.
okay, sir. Okay.
And in week 5, we have discussed about the different techniques to get the small signal model. So I'll not go in details of the model. I'll just browse through what models we have discussed. So I have first explained the circuit averaging technique, where we will average the dynamics and then we'll get circuit for each of the inductor dynamics, capacitor dynamics, as well as the input current dynamics, and then we'll club everything. This is called equivalent circuit model. And same thing we can do with the average switch model, where the switch is averaged and then the average switch model is connected in the circuit itself. Irrespective of the method, you will get the same circuit. So whichever is easy for you, you can choose and stick to that. But as a student, you are learning, you should learn all the methods. Once you learn, it's up to you which method you will be using, which method you are comfortable with. Some people are comfortable with state space averaging. Some people are comfortable with circuit averaging. Some people are comfortable with average switch model. And then from this, we have also understood if you remove the AC perturbation terms, then it becomes a DC equivalent model. If you remove the DC terms, then it will become AC equivalent model, from which we can get the small signal transfer function and we can design the controller. So we got the DC equivalent model, and I have asked a few questions based on the efficiency as well as the voltage gain. And we have done the same for parasitic buck converter with parasitics, and then we have also gotten the expressions for the same. As time permitted, I have also discussed about the state space averaging, where you do the averaging on the state space and then you get the small signal model as well as the DC operating point. Here you cannot visualize the circuit, but this will be more helpful when the order of the system increases, because then you cannot have multiple number of components and then analytically or mathematically calculate the expressions. Then it becomes easy to give it to computer like MATLAB or any other software, where you will just give in the matrices and it will do the calculations for you. So it will become more systematic. So depending upon the requirement, we can choose either one of the methods. But it's not that you have to learn this method or that method. All methods are equally important. You can choose any one of them. You'll get the same answer. So that is all about week 5, like simple and straightforward modeling techniques. If you have any doubts, you can ask us and proceed to week 6. Okay. So in week 6, we have started with the AC equivalent model because in the previous week we have discussed about the DC equivalent model. So here we got the AC equivalent model. And then I have mentioned why DC equivalent model is needed because in order to calculate the operating point efficiency as well as losses, AC equivalent model is needed to get the small signal transfer function, which we can use for the controller design and check the transient performance. So once we get the AC equivalent model, we have learned how to get the different transfer functions. One is the input impedance, output impedance, audio susceptibility, and control to output transfer function. All these 4 transfer functions are very important in respect of your field. The terminology remains same. So as long as control is involved, these transfer functions will be there. So don't mug up the expression, but understand like input impedance. So input impedance is input side and impedance. So V in by I. Similarly, output impedance is V naught by I naught. Audio susceptibility is input and output voltage ratio V naught by V. Control to output is control D to output V naught. So V naught by D perturb. And the other perturbations will remain 0. And we have calculated the transfer functions for buck converter, and then the same thing can be extended for boost. I think Kelvin might have explained that. So now I have considered a practical buck converter and I have asked the same transfer functions. Now it becomes more difficult because of the additional parasitic that comes. But I have not simplified it, but you can simplify it as far as given the final expression. I have just made you understood the process so that you can do it for any converter. So we have decided we'll leave it at the final expression and not go into the details of the maths where you can spend time and do which will be needed for your exam. Then we have also asked what is the small signal block diagram where we'll have all the transfer functions connected and then we'll have something like this. So this is the small signal block diagram. Now this V naught button will pass through reference error generator and then pass through the controller and that will close the loop. So till this week we have understood the modeling aspects and how to get the small signal transfer functions and what is the controller loop diagram. Now using this we'll design the controller in the upcoming week. So that's how the flow is going. So in this week, we have discussed about this, and also Sir has discussed about current mode control expression. So I have also taken one problem where we'll solve the expression for control to output transfer function under peak current mode control, and we have gotten the first order system. If it is second, like non-ideal case, then we'll get additional 0, but still first order. So that's why it is ordered, and current mode control can be approximated as a first order. So till now we have gotten the models, but we are not sure whether they are correct or wrong because we need to validate. So that sir has shown in the upcoming weeks how to validate it, but in this week we have learned how to get the models. So any doubts till week 6? Okay, I guess no. So in week 7, we have started with that closed loop block diagram, and then we have started designing the controller. So in the voltage mode control, how the loop will be closed, and we are doing loop shaping approach. So the loop transfer function has to be considered, and then if you do pole zero cancellation, how the controller gains will look like. And we have also discussed about one important aspect, which is the ideal versus practical PID controller, because ideal PID controller cannot be implemented because it has an improper transfer function. In the case of practical PID controller, we'll consider very small tau d, so that basically tau ds plus 1 can be approximated as 1 because tau d is very, very small. And then now this is a proper transfer function and it can be implemented. So we have seen how if you do pole zero cancellation, then how to get the K1 and K2 gains. And we have seen the phase margin is always 90 degrees. So if you want to have additional freedom, then you have to use type 3 compensator. So we have solved one problem and we have gotten the the practical PID controller gains and how to solve that from based on the transfer function. Now, if you use type 3 compensator, it has an additional pole. So the phase margin is not 90 degrees and it can be controllable, which is not the case of the normal practical PID. So in this case, we have the freedom to change both phase margin as well as the bandwidth, and we have done the same thing. So we have derived the expressions if phase margin needs to be changed, if bandwidth also needs to be changed, how to get the gains. Then we have quickly solved one problem where I have given bandwidth as well as phase margin, and how we can decide the design the type 3 compensator to achieve both of these, and we have solved the problem to get the gains, and this is the overall type 3 compensator. If in your free time you can also do the same and then run the simulation and check whether it is able to get achieve the same bandwidth as phase margin also. It should be. So you can do that also during your free time. So in week 7, it's all about voltage mode control. We have discussed the pole zero cancellation based controller design. I have discussed about buck converter, boost converter. Calvin has discussed. So we have discussed about the practical as well as ideal PID controller and why we need type 3 compensator to have more flexibility. So if you have any questions in week 7, you can ask. Else we'll move to week 8, which is about current mode control. Okay, I guess no. Then we'll move to week 8. In the case of week 8, we have started with the current mode control, and we have closed the loop and see how we are getting the overall closed loop block diagram. And before we proceed with any model, always remember this: we have to check whether the model is able to capture the dynamics or not. Because if the model itself is not accurate, then that controller that we are going to design will not be also accurate. So it will not have the bandwidth and phase margin that we are targeting for. So the model accuracy is very, very important. So we have considered here approximated first order model. So we have also discussed if we want to use more accurate model, then how to do. So in the case of more accurate model, we have generalized. So we have considered the ramp compensation as well. And then now we have considered the average dynamics of the current. And there are two methods. In first method, we have assumed that the average is same in the cycle. Whereas in the case of second case, we have considered the average this and this is also varying. So we have considered the average on this side plus average on this side, and then we have added. Whereas in the case of method one, we have assumed that at least in a cycle it is fixed. Here we have considered that this and this point may not be on the same line. So this is also varying. This is also varying. So we have considered more generic and more accurate model, and we have gotten 3 such models. So in this case, I have given you this table because every time you cannot derive the expression. So I have given you the table where you can see and remember these final expressions which may be needed for your final exam. But sir has shown that the first order approximated model is quite closely matching the dynamics. So now it boils down to 2 things. One is the accuracy and the other one is the simplicity. First order model is simpler because it is first order and reduced order. First order is simple. And then it is also quite accurate in capturing the dynamics. So we can use that only rather than using much complicated higher order model, which is also matching the dynamics in a similar way. So we'll use simple as well as accurate model, quite accurate. And then we have used that model to design the controller using pole zero cancellation. So I have given you one problem where you have to design the controller, and we have designed the controller. Because it is first order, things become very simpler. Again, if you use PI controller, phase margin is always 90 degrees. In order to have control over a phase margin as well as bandwidth, you need to have type 2 based controller where you'll have an additional port which will give the flexibility to tune bandwidth as well as phase margin independently. So we have also asked one question based on that how to design the type 2 compensator. It's all pole zero cancellation and getting expression for bandwidth and phase margin, and then we have gotten the final expression. So in week 7 we have discussed about voltage mode control design. In week 8 we have discussed about current mode control design. But we have identified that in either of the methods or approaches that we have used the small signal model where we have made approximations. So there will be, of course, some limit in terms of the model, which comes from the bandwidth. So the bandwidth is limited to 1/10 of the switching frequency. But if we want to achieve higher bandwidth, then we can no longer use that model. And then we have to use a better model, which is, of course, not derived without taking any approximation. So we have seen how to consider the large signal model. But before that large signal model, we have to understand that how to identify the equilibrium points, how to get the vectors field, the shape of the trajectory, how the trajectory is moving, etc. So in week 9 we have discussed about this before we move to week 10 where we have discussed about the trajectory based control design. So in week 8, do you have any questions until week 8? Okay. So if you don't have any questions, then I'll start with week 9. So in week 9, we have learned about the average nonlinear model using Taylor series expansion. So we have considered a nonlinear model and linearized it or averaged it around an operating point, and we have seen what is Jacobian matrix and how we can get the other set of matrices. And I have given like everything together, so you can directly go through this. And then we have seen first order system if you want to get the dynamics, how the dynamics will look like, and based on the initial condition and coefficient A, how the trajectory will look like. So this is stable because it is tending to zero. This is unstable because it will keep on increasing. So we have commented on the stability, and I have given one problem where you have solved and saw the whether the system is stable or not and how the x of t is varying with time. Then we moved on to the second order system, first decoupled system, and we have seen how to calculate the eigenvalues. Based on these eigenvalues, how can we comment about the stability? So we have also discussed about eigenvectors, how to calculate the eigenvectors. And then I have discussed about few cases of the second order system. First of all, these eigenvalues are real. If they are imaginary, then there are other set of possibilities. So if they are real, which I have mentioned here, there can be stable node, unstable node, and saddle point, and these are the possibilities of real eigenvalues, and these are the uh, trajectory with time. And if they are complex conjugates, there can be unstable focus, stable focus, as well as center. And we have also seen how to get the direction of the trajectory, whether it is going in clockwise or anti-clockwise. You need to calculate the vector field. So you have to consider delta x and then calculate the vector field. So x dot, you have x, say x dot is ax. X you can consider delta x1 and delta x2 and calculate delta x dot. That will give you the direction based on whether it is going in anti-clockwise or clockwise. So here we have considered one decoupled system as well as coupled system, and we have solved for eigenvalues as well as eigenvectors and how to get the transformation matrix. So if two systems are having the same eigenvalues, then using the transformation matrix M, we can get A and B relation. So that transformation matrix also we have obtained how to get the transformation matrix, and we have seen that we can be obtained using this expression. And then we have also seen the stability of the nodes, whether it is saddle point or stable node, unstable node. And if we start from certain point, how the trajectory will reach the equilibrium point. If we also calculate the eigenvector. So this orange color is the eigenvector, and eigenvalues are both less than zero, so it is stable, and how the trajectories move. And then we have solved another problem where I have asked you to calculate the equilibrium point. So if it has multiple equilibrium point, at each equilibrium point, we have to find the A matrix. From the A matrix, we need to find the eigenvalues. And from the eigenvalues, we can comment on the stability. Now, if you want to know the trajectory, then you have to calculate the eigenvectors. And for these eigenvectors, for those eigenvalues, how the trajectory will look like. So here I have mentioned how to calculate the direction, whether it is anti-clockwise or clockwise. So you have to consider delta x, and then now if it is minus delta x and 4 delta x, so it is in this direction, so it is flowing in anti-clockwise. So in one case we have got an unstable focus and it is moving away in anti-clockwise direction, whereas in the other case it is saddle point, so there is no question about the direction of the trajectory, anti-clockwise or clockwise, but you have to identify which is the stable eigenvalue, meaning which is the stable axis, which is the unstable axis. So along the stable axis, it will try to move to the origin, but once it moves, the unstable axis will make sure that it will move away towards the infinite. So this is called saddle point. And then we have solved one final problem based on the transformation matrix. If I given you the original system and applied a similarity transformation, how it will like how to calculate A dash, B dash, C dash, and D dash. So this is also simple. So there is less than a minute. If this meeting ends, kindly join back. So week 9 is all about operating points, their stability, eigenvalues, eigenvectors, and how to get the trajectory details and A matrices, all these things. So any doubts till week 9? If this meeting ends, kindly join back. Okay. So in
Sir, so
yes.
One doubt regarding that eigenvector, drawing
Yes.
eigenvector in the two-dimensional space.
Okay.
Suppose if the eigenvector is 1, 0, we will mark it in x1 axis.
Yes.
If it is 0, 1, we will mark it in the x2 axis.
Yes.
But in some cases, we get complex eigenvector like 1j. So,
Yes.
is it correct to mark it like 1, 0 plus j into
Yes. Yes.
0,
Yes.
1 and
Yes.
then
So if you see, maybe in this question, so here we got 1 plus I and 1 minus I. So the vector is 1 and minus of 1 plus I. So here what happens is like you cannot actually, this is unstable focus. So we cannot visualize in this like in this real dimension. So here it's not exactly related to the eigenvectors, because once the things are complex, the only three possibilities are stable focus, unstable focus, and central. So in all these three cases, it is moving in a circular direction. Either it is in the same circular direction, not moving away or towards the equilibrium point, which is the case of center, or it is moving towards the equilibrium point or away from the equilibrium point. So unlike these cases where you need to know the eigenvectors, here you need not know the eigenvector where it is located, because it is imaginary. So only thing here you need to know is the direction, which you can get from the x dot. So I am considering delta x perturbation, and minus delta x is corresponding to left side, and this is corresponding to upside. So the like effective will be in this direction, northwest, so it is going in anti-clockwise direction. So the imagining the eigenvectors here will not be of any helpful, because anyway it is either going in circular fraction inside or outside. It's a real dimension, so we cannot
okay,
have the imaginary dimension.
okay, sir. Okay.
Okay, so in week 10, I have just given a summary of previous weeks just to connect the dots, and every week you should know why we are learning this, because that is more important than what you learn. You should learn why you are doing this, how you are doing this, how it will be helpful. So here I have mentioned that in order to use large signal model, we have discussed about the trajectory and everything. So that's why trajectory, phase portrait, equilibrium points, and stability is very important. And then Sir has discussed about the sliding mode control, and later we have used time optimal control. So in sliding mode control, it will slide across the surface and will reach the equilibrium point. So we have discussed what will be the order of this switching surface, and what will be the slope, etc. But in this case, the switching is infinite, which is practically not possible. So we need to have a hysteresis band. So in this band, it will move and it will reach the steady state point. So here we have few preliminary questions. What are boundary points? And I have explained what are boundary points and how the trajectory will look like in each of these points. And which is chattering behavior. Chattering behavior is this infinite frequency where it will just have like switching, infinite frequency switching, which is practically not possible. So that's why we have kept this band. And then we have also asked few questions on the switching surface. Usually the switching surface, number of switching surfaces will be equal to number of inputs, and the order of the switching surface will be one less than the system. If the system is second order, then it will have one dimension. If the system is third order, then it will have two dimension, which is a plane. If the system is fourth order, then it will have three dimension surface, which is a surface. But if we have two inputs, we have two such surfaces. Here also we'll have two such planes. Here also we will have two such lines. So number of switching surfaces is equal to number of inputs, and the dimension of the switching surface is one less than the dimension of the system. Then we have taken one problem, and if u is of switching between 8 and minus 8, then the switching surface is this. Then we have asked what are the equilibrium points. So we have to find the equilibrium points, because it is dependent on you. We will get two such equilibrium points. So one equilibrium point is minus 4 comma 0 here, and the equilibrium point is 4 comma 0. So now I have asked what is the dynamics if it is sliding on the surface. So if it is sliding on the surface, then my system should satisfy this as well as this. So sigma x is c into x1 plus x2, and x2 is nothing but minus x1 dot. So that we have substituted and solved, and then we have seen if c1 is positive, then the system is stable, because then it will move towards the equilibrium point. If c1 is positive, then x1 will keep on increasing, so it will move away. So on the surface also, it can move towards the equilibrium point if it is stable, or away from the equilibrium point if it is unstable. So we need to see what are the condition. for which the system is stable. So if C is negative, which means slope is, C is positive, then the slope is negative, then the system is stable. If C is negative and the slope is positive, system is unstable. And then we have also seen in the case of time optimal control, how the trajectory will look like and how we can correlate with the inductor current, capacitor current, and output voltage like waveforms. And using this, how we can solve for the time and how we can apply capacitor charge balance to get the details of the I peak and delta V undershoot. So we have done capacitor charge balance, and then we have gotten the I peak expression in terms of duty ratio as well as the V undershoot in terms of duty ratio. And then we have quickly solved one problem where I have given certain condition and I have asked what will be the settling time, what will be the peak current, and what will be the voltage undershoot. And we have used these derived expressions to calculate this. So it is very simple. So in week 10, it's all about sliding mode control and how we can derive the expressions for the time optimal control. In week 11, it's more about how to design the PID controller for the last signal tuning for both voltage mode control as well as current mode control. And then in week 12, it was more about summary and digitization. So if you don't have any queries in week 10, I'll move to week 11.
Sir, here we have derived an expression for delta V0.
Yes.
And this. And in the subsequent week, there is another expression for delta, like V1 equal to V of minus.
Yes, yes.
So when I tried to compare this, it was not
Both
matching.
are not matching.
So
Yes,
let me
yes. That's a yes, yes. Both are not matching. That's a very point that you have identified. So here, in this method, what we have done is, if you see the M1 slope, we have assumed that it is constant, but it is not constant because V0 is changing, right? So we have assumed M1 and M2 are constant, whereas M1 is dependent on V0, V in minus V0 by L. M2 is also dependent, which is minus V0 by L. So in this case, this is one approximation that we have considered because the slopes are changing as V0 is changing. So in our calculation, we have considered M1 to be constant, but this is slightly varying. So the answer that you will be getting will be slightly different from what it ideally should be. So this method is not as accurate as what we have done in the upcoming weeks, where you have considered the trajectory and not considered any expression based on M1. Rather, you have solved the dynamics of the system without making any approximation. So you are right, the expressions will not match. This is easy, but not as accurate as what we have discussed in week 11, which is more accurate and also a little bit cumbersome when it comes to the calculations.
Okay, sir. Okay.
Yeah, that's a very good point that you have raised. In week 11, we have discussed about first PID controller, how the PID controller will have effect on overshoot, settling time, and steady state error. So this is very important. So we have again revised that why we need practical PID controller and why ideal PID controller cannot be implemented. And then we have seen how the PID gains are affecting overshoot, settling time, and steady state error. So this is very important. If you have any queries, you can go through that week's lecture. And then we have started solving few problems, and then in the problems I have tried to explain the concept. So characteristic impedance is nothing but square root of L by C. So once we got this, then we have moved to another problem. So here what we have asked is for a load step change, what will be the proportional gain for optimal recovery? What will be the value of peak current? What will be the voltage undershoot? So here, whatever formulas that we have used, sir has derived considering the trajectory without making any approximations. So the expression for I peak and V1 will slightly differ. But if you calculate, the difference will not be drastically much. So in the previous method, it's more simple, but not completely accurate, but it is very closely accurate because only M1 and M2 will slightly change. Whereas this method, it is very complicated, but it is accurate because we have not made any approximation. We have considered the actual trajectory and solved for it. So once we taken these expressions from Sir's lecture, we have not derived, we didn't get time for derivation. Then we have solved a couple of problems for load step up transient as well as load step up step down transient. What are the undershoot overshoot we have calculated. And then we have moved to another case where step down I have given. So yeah, in the previous question, there is no step down. We have considered two cases for step up. In the next problem, we have considered step down and we have asked what is the proportional gain. So as there is no expression derived for voltage overshoot, we have not gone to voltage overshoot, but we have just derived the proportional gains. And then we have also discussed about the dynamic voltage scaling. And I have given some practical example about processor and how dynamic voltage scaling is needed. Sometimes we need to change the V reference from certain value to certain value. And in such cases, what will be the delay and dynamic power consumption based like related to that VDD. And we have solved one problem where we have considered two processors with the two different conditions, and we have seen which exhibits or which consumes more power and which exhibits a higher time delay based on the relation. And then in the final problem, we have seen for reference tangent and step load tangent, the requirements are based on the small capacitance, large capacitance, or small inductance and large inductance. And we have seen that there is a trade-off. If you are targeting reference transient, you need small capacitance and large inductance, whereas for step load transient, you need small inductance and large capacitance. So there is a trade-off, because if you are optimizing one, then you are suffering with the other. So there is again a trade-off. So you will get decent transient response and near time optimal load transient response. Accordingly, you have to choose inductance and capacitance. So there is always trade-off. So we have used this matching to identify the trade-off and then see from where this trade-off is coming, and get more understanding about which type of inductance and capacitance needs to be used for optimizing what transient response. So that was all about week 11, where we have identified the proportional gain for optimal recovery, as well as undershoot and peak current like expressions for step up response, and proportional gain for step down response, and also dynamic voltage scaling, and how the optimal response parameters are dependent on inductance and capacitance. So if you have any queries, you can ask. I'll just quickly summarize week 12 as well. Okay. So in week 12, sir has mostly summarized what he has discussed in the previous weeks, and also motivating for the digital control, why digital control is needed, why it is the future. So I have also quickly summarized what we have discussed in the week 11 till week 11, and then what type of modulation techniques that we have learned, what type of aspects that we have learned, like stability, design, performance, protection, etc. And what type of modeling techniques that we have learned, small signal based, large signal based, and what is the difference, which needs to be used where, and different modes of operations like CCM, CRM, DCM, and then different models like AC equivalent model, DC equivalent model, and why it is needed, and what type of architectures, control architectures we have learned, like voltage mode control and current mode control. And in either of the cases, we have learned small signal model and validation, small signal based controller design, as well as large signal based controller design. In the case of voltage mode control, you will be needing PID or type 3, whereas in the case of current mode control, PI or type 2 is sufficient, because here the model is second order, here the model is first order. And also in large signal tuning, we have seen the trade-offs between the reference as well as load transient in terms of choosing capacitance and inductance. And we have seen that if the undershoot is reduced, capacitance is reduced, power density will be increased. Also, the settling time is reduced. Also, the number of switchings during the transient is reduced. So the uh, performance is also optimal, and also energy efficiency is also optimal. And then we have solved one problem where characteristic equation is given, and we have to calculate the characteristic equation and design the PID gains of GC. So we have calculated the characteristic equation and compared it to get the gains. And now I have given another problem where I have multiplied the DC gain by 10 and see to see how the gains will change. So if we do any multiplication, then it has to be divided to maintain the same characteristic equation. So the gains are divided by 10. Now if I uh, incorporate an additional sensor gain of 0.5. So basically we are multiplying by 0.5. So we need to divide by 0.5. So from here we have to divide by 0.5 to get the final gains. So this is just to give you the idea about how the gains in the loop bandwidth are affecting the KPKI KD values. In the next problem, we have considered one PI controller, and we have solved for the PI gains. Once we have solved for PI gains, I have given if the sensing gain is 0.1, we have to divide by 0.1, which means we have to multiply by 10. So if there is any gain, you need not recalculate everything again. You just have to understand that you need to divide the gains by whatever factor that you are getting, so that the same characteristic equation or the same bandwidth and phase margin can be achieved. Then we have learned about the digitization aspect of the analog control, where I have highlighted what are the additional blocks that are coming into picture. So we have studied about ADC, where the first question is at what rate we need to sample, because that can lead to limit cycle oscillations if we are doing oversampling, or will lead to subharmonic oscillation if we are doing undersampling. And also the delay will also have an effect on the stability of the system. Then we have discussed about the finite resolution effect caused by the digital PWM, because we have here counter, so that is quantized in terms of time as well as the value. So we cannot have every value. So what happens if the resolution is finite, and if we don't have that value, so then it will oscillate between two values, so that it will never reach the steady state. There will be some oscillations around the steady state. So here we have considered one in terms of time aspect, which is duty ratio. In another one is the control voltage, where if this control voltage coming from the controller is not exactly aligning with these levels, then again it will also oscillate. So the steady state, around the steady state, there will be oscillations. Now, depending upon how fine this resolution is, the oscillations will become that small. If the steps are big, then the oscillations also will be big. But we have also discussed, if there are so many issues, why do we need digital control? So first of all, it is immune to noise, and the PID gains can be changed anytime. You just have to change your vanilla code and dump in the FPG or in your IC. And also there is no aging, because it's a digital control. It's everything inside the IC, unlike physical resistance and capacitance. Also, the tolerance of RNC will not affect the PID gains. Once you fix it, they are fixed. And also we can change the gains in real time, and we can make it, you know, uh, more smart, so that it can change the values depending upon the situation. And also we can implement complex algorithms by writing the code, vanilla code, and synthesizing it to an IC, rather than using op amps and implementing using op amps, which will have a lot of space, as well as the price will also increase, and also the difficulty will also increase, which can be implemented in a single IC using digital control. And then we have discussed about the digital voltage mode control architecture, and I have just given the expression about the PID controller for both continuous time as well as discrete time, but we have not gone in details because that is not part of this course. But just to give you idea about how things will look in continuous and discrete domain, I have just given the expression, but this is not part of this course, so we have not spent much time. So that is all about this course. Just a brief summary, surface level summary about what all we have discussed. If you have any queries, I'll address, else we can wind this session. And I wish you all the best for your final exam. Please be thoroughly prepared with all the assignments, go through the solution, find out where you have made mistakes, solve multiple times, so that you are more comfortable with the calculations, and you do not make any calculation mistakes. So that's the only key. Try to understand the concepts, go through the lectures or problem solving sessions, solve as many problems as possible. Be confident. First, answer the questions that you know, and then you will get time once you solve all the known questions. Then you see which are easy in the unknown questions, and then you try to attempt. If they are very difficult, leave it. Don't bother about that, because that you can solve towards the end. So first start solving all the questions that you are confident about, and then you can solve the difficult questions. So the exam paper will be evenly distributed. There will be 70% easy, 20% medium, and 10% difficult to create the differences among the students. So most of the questions will be assignment based. So if you have thoroughly solved the assignments and you are confident about assignments, you should be able to solve 80% easily if you don't make any mistakes in the final exam. So any more queries? And also I think Kelvin session will start now, 7 o'clock, 7 to 8. So uh, yeah, if you have any questions, you can ask, else we'll wrap up this session so that you can join this session as well.
So can we get this the whole PDF?
Yes, yes, yes. Yeah. Okay. Thanks for asking. I'll upload the video today, and then in that I'll in the my that what is in the description, I'll give you the link so you can access. Also, I'll upload it to the Google Drive access you have. So I'll do this. Okay. By tonight, I'll try to upload this video, and I'll give you the link. So by tonight, you should be able to get. So please go through my notes. If you find any mistakes, you can let me know so that I'll update and then give you, or maybe I'll rectify in the description so that people will be aware.
Thank you, sir. All the sessions were very helpful for solving the assignments. Thank you very much.
Oh, thank you. And I also
Yes,
thank
sir.
you for
Thank you,
being
sir.
interactive.
Thank you, sir.
Thank you. Thank you. I wish you all the best. If you have any queries, you can approach me and yeah, try to solve as many problems as possible. Okay, you can join Kelvin's session now. I wish you all the best. Thank you and good night.